Okay. So, we have learned about fuzzy set. Fuzzy set is the basic element in fuzzy system. Today, we are going to learn about the different operations on fuzzy sets. So, the different operations on the fuzzy set in many ways similar to the operation those are applicable to the Cripps set. This is the normal set that we have learned in set theory. The operation those are applicable there in Cripps set such as union, intersection, complement, all those things also are applicable to the fuzzy sets, but the definition of all these operations are with different implications. So, we learn one by one the operations on the fuzzy set. So, let us first discuss about the union operation of two fuzzy set. Now, here A and B are two fuzzy sets suppose. So, union of two fuzzy sets is denoted by the symbol cap. This is the usual symbol that is used there in Cripps set. So, A cap B denotes the union of two fuzzy sets A and B. Now, the union operation whenever it is performed on the two fuzzy set, it will basically give the membership functions for each elements which are belongs to the union of the two fuzzy sets. The membership values for different elements in the union of the two fuzzy set is defined by this expression. So, if you see this expression, so union operation for any element x which belongs to the union of the two fuzzy set A and B is basically max of mu A x and mu B x, where mu A x denotes the membership values for an element x belongs to fuzzy set A and mu B x denotes the membership value of any element x belongs to fuzzy set B. Now, let us have an example. Say here A is a fuzzy set which is defined with the different membership values for different element shown here. Similarly, B is the another fuzzy set. Now, the union of two fuzzy set is denoted as C, which is A cap B is basically this is the fuzzy set. So, union operation gives another fuzzy set. Now, here we can see how we have obtained the membership values for the different elements which belongs to the set C. So, here 0.5 it is obtained as the max of these two values 0.5 and 0.2, it is as per the definition. Similarly, 0.3 it is basically max of the two values membership values they are in the set A and B and likewise. So, this way we can obtain the union operation of the two fuzzy sets. Now, the same thing can be better explained with the help of a graph. So, here we see the graphical representation of two fuzzy sets A and B. So, graphical representation means it is basically representation of the membership function how they change with the different values of element belongs to the two sets. Say here the two sets with the universe of discourse. So, this is basically the universe of discourse of the two sets and the fuzzy set A is defined by its membership function for the different element which is denoted here. This is the membership element membership function for the fuzzy set A. Similarly, this denotes the membership element for the fuzzy set B. Now, as the union operation is basically max of the two values. So, up to this portion, so this is the B and this is A. So, the max is this one. So, this basically the union up to this part and then so union of this and this basically the max. So, it is this one. So, this part is the rest of the value up to this one. So, this way we obtain the membership function of the union of the two fuzzy set which is represented by this graph. Now, let us discuss the intersection operation. Intersection operation of two fuzzy sets is denoted by this symbol, it is cap. So, So, here and the membership functions of the resultant fuzzy set A cap B is denoted by this expression, and you can say in case of union it was max, whereas in case of intersection we have to take the minimum of the two values of the membership for which the A and B belongs. Now, as an example, A is the another set and B is the another set, and the intersection of the two set is represented here. Now, here whenever we go for intersection for the element x 1, then we have to take the minimum. So, we take the minimum from here. So, it is the minimum. So, here 0.1 which is in A and 0.3 for x 2 which is in B, and in the union operation where the x 2 has the value minimum this one. So, 0.1. So, this way we can obtain the intersection of two fuzzy sets. Now, the same thing again can be drawn graphically. So, this is the fuzzy sets A and this is the fuzzy sets B, and we have to take the minimum of the two. So, for up to this part minimum of A and B, it is basically this one. So, we can obtain this part, and for the rest minimum of this one is this one. So, we can take this one. So, this graph basically shows the membership functions of the union of two fuzzy sets A and B. Now, another operation on the fuzzy set is called the complement. The union operation and intersection operation are the binary operation, because they needs two fuzzy sets, whereas the complement operation is a unary operation which is applicable to only one fuzzy set. The complement operation on any fuzzy set A is represented by this symbol A superscript C. So, it is basically a complement of the fuzzy set A, and the resultant value of the membership functions is defined by this expression mu A C x, that means, is a membership function of the resultant fuzzy set A C, and it is denoted as 1 minus mu A x, where mu A x denotes the membership function for the fuzzy set A. Now, this is an example. So, A is the fuzzy set and then its complement A C is like this. So, for x 1 we have to take the this formula 1 minus mu x. So, it is 0.5. So, for the 0.1 it is 0.9, for 0.4 it is 0.6. So, the complement operation is straightforward. The same thing again can be shown graphically. So, this is the fuzzy set for this is the fuzzy set A, where the membership function is like this. Now, its complement. So, the complement value of this is basically this one, and complement value of this basically this one. So, the resultant value of the membership function for the complement A is basically this one. So, this way the complement operation can be obtained. Now, so these are the very simple operations: union, intersection and complement. There are few more operations. The first operation in this context is called algebraic product or vector product. Now, algebraic product or vector product is denoted by a dot symbol. Algebraic product or vector product is denoted by the dot symbol A dot B, where A is a fuzzy set and B is another fuzzy set. So, the membership function for the resultant fuzzy set is denoted by this, and it is obtained using this formula. It is basically simple as a product of the values of the membership functions belongs to fuzzy set A and B. Now, if A is a fuzzy set x 1 0.5 and x 2 0.3, this is the fuzzy set, and B x 1 0.1 x 2 0.2, then the mu A dot B x for C that can be obtained. So, x 1 and it is basically product 0.5 and 0.1. So, it will give you 0.05. Similarly, x 2 it will give you 0.06 and so on. So, this way the product can be obtained. Now, so this is the vector product. Now, like vector product is a scalar product where alpha is a constant. Alpha is a constant usually value in between 0 and 1 both inclusive. So, the scalar product of a vector A is denoted by this formula mu alpha A x, where alpha A is a basically scalar product of the fuzzy set A and its new membership value is defined as is a product of alpha and the membership values of the function A x. Now, there are few more operations, one by one let us discuss them. So, the first operation is sum of the two fuzzy set A and B. It is denoted by the sum of the two fuzzy set A and B is denoted by A plus B plus operation, and its new membership function is denoted by this expression. It is easy to evaluate. If we know the mu A x for the fuzzy set A and mu B x for the fuzzy set B, then mu A plus B for the fuzzy set A plus B obtained using this formula. Now, the difference operation on two fuzzy set A and B is denoted by this notation A minus B, which is equivalent as the A intersection of B complement, and it can be obtained using this expression mu A minus B, that means membership value of the difference of the two fuzzy set A and B is same as the membership values of A intersection B complement x. So, if we can calculate, so better idea is that we can calculate the intersection of A and B complement and then the mu can be obtained easily from there. Now, their disjunctive sum, it is denoted by this expression A XOR B like, and it can be obtained using this one. So, A C intersection B union A intersection B complements. So, this means that if we know these operations first and then this operation, then we will be able to calculate A XOR B. Now, this is the disjunctive sum. Next is bounded sum. Bounded sum expression is basically denoted by this, where A and B are the two fuzzy sets and the membership values of the resultant fuzzy set, it is denoted by this, it is basically obtained using this formula. So, it is basically take the minimum of 1 and the sum of the membership values of A and the membership values of B, fuzzy set B. So, this is bounded sum, and another is bounded difference. The bounded difference is expressed by this notation and its membership value can be obtained using this formula. It is the maximum of the values 0 and mu x plus mu b x minus 1. So, we can take the maximum of these two values for each element x, then we can obtain the fuzzy set membership values of the elements which belongs to the bounded difference. Now, equality and power, these are the other two fuzzy sets. We say two fuzzy sets A and B, they are equal, and it is denoted by this expression A equals B. So, two fuzzy sets are equal if for all elements belongs to the set has the same membership value. So, which is represented by this expression. Now, power of a fuzzy set which is denoted as A alpha, where alpha is a constant any value, then the resultant fuzzy sets whose membership value can be obtained using this expression, where this is the membership values of the resultant fuzzy sets and mu x is the original fuzzy sets and here mu x to the power alpha. So, it is a exponential operation that can be applied for each elements belongs to the set x, then we can obtain the resultant membership values belongs to set A alpha. Now, you can note if alpha is greater than 1, then it is called the concentration, and if alpha is less than 1, it is called the dilation. So, these are the two operations that is possible for A and B. Right. Now, another operation which is very much frequent operation in fuzzy logic, it is called the Cartesian product. The Cartesian product of two fuzzy sets A and B is denoted by this notation, and its membership function is denoted by this notation. Now, we can note the operation, it is basically mean of A x and B y. Now, here again product, whenever we say the product, it is basically is a product for all elements. Now, for an example, suppose x is the A is the fuzzy set which is defined over a universe of discourse x, and B is the another fuzzy set which is defined over another discourse y. Then the product A cross B can be defined using, so here x 1 and y 1 and then take the minimum. So, it is basically 0.2 and 0.8. So, 0.2. So, this can be better represented by means of a matrix. So, all the elements which belongs to the set A can be represented here, and all the elements which belongs to the set B can be represented here, and then x 1 and y 1. So, x and y 1 and take the minimum in between, x 1 and y 2, x 1 and y 2 is basically taking the minimum of 0.2 and 0.6. So, it is 0.2, then x 1 and y 3 0.2, minimum of 0.2 and 0.3, it is 0.3. Similarly, for x 2 y 1, x 2 y 2 and x 3 y 3. So, this element will be obtained. So, the Cartesian product can be expressed with the help of this kind of matrix, and it is called the relation matrix. Regarding the relation matrix, we will learn many things in a later stage. So, this is the operation that can be performed as a Cartesian product. And one thing you can notice, the union, intersection or whatever the operation that we have discussed, they basically applicable on two fuzzy sets A and B, and all the fuzzy sets A and B, they are defined over the same universe of discourse. Whereas, the Cartesian product can be applied to the fuzzy set, they can be over the two or the same universe of discourse. Now, the operations those we have discussed, they follow certain properties. The commutative property that it is basically A intersection B is same as B intersection E. This is called the commutative commutative property over the intersection, and this is the commutative property over the union operation. Likewise, it is called the associativity, that means this and these are equivalent, or this and these are equivalent. The distributive property also, if A union B intersection C is same as A union B and intersection of A union C. So, it is basically A is distributed over B and A is distributed over C. Likewise, for this operation also. So, whenever the many operations are involved and they can be applied on two fuzzy sets, then they satisfy these are the properties it is there. There are some other properties also, it can be applicable there on the fuzzy sets. Other property like idempotence, that means if A is a fuzzy set and if we take the union of the same, it will give you the same fuzzy set A. Similarly, A and intersection of A, it will give you the null fuzzy set phi, and these are the thing is simply understandable. Now, transitivity is basically if A is a subset of B and B is a subset of C, then we can say that A is a subset of C. So, this is the similar operation that is applicable for the Cripps set. Now, involution, this operation is if we take the complement of the same fuzzy set, then it will return the original fuzzy set. The De Morgan's law we know, which is there in Boolean logic as well as the Cripps logic. So, it is basically A intersection B, and if we take the complement, it is same as A complement union B complement. Alternatively, if A union B take the complement, it is equivalent to A complement intersection B complement. So, these are the properties, those are whole good for fuzzy sets. These properties are very much useful whenever we want to perform many operations on the different fuzzy sets. And one thing we can note, the operation that we have discussed about, it basically if two fuzzy sets are given, then how we can obtain another fuzzy set. So, if A and B is known to you, then we can obtain another fuzzy set C. Now, if we know C, then we can use another operation to find another. So, those operations are basically produce many other fuzzy sets from the given fuzzy sets. Now, I would like to elaborate the fuzzy set operation more clearly with some figures. Is basically called the graphical representation. So, sometime in order to understand the fuzzy operation, graphical representation of the two things is more useful, and there are many tools which basically follow the graphical way of representing fuzzy set and then performing their resultant operation. Now, here first example, here this is the membership function of. So, this figure shows the fuzzy set A, whose membership function is shown by this graph, and another fuzzy set B, whose membership function is shown using this graph. Now, we want to find many operations like say union, like say intersection, whatever it is there. Now, in order to find the union or intersection or complement, of course, complement is not required here, only say union and intersection, let us suppose. Then best idea what is, we can draw the two graphs on the same graph. Now, for example, if we draw the graph of the two graphs, the resultant graph will be obtained like this. Now, once the resultant figure is available, then we can easily identify if the union or it is the intersection of the fuzzy sets. So, here if this is the graphs of the two fuzzy sets on the same plot, then we can have the union operation, it is basically union operation. Union operation we take the max of this one. So, up to this part, this is the max part, and then this for the next part. So, this way this is the union resultant, this one. Similarly, for the intersection we take the mean this and then this. So, basically this is the graph for the intersection. So, what I want to say that if we can plot the membership function of two graphical representation, then from there we can obtain the resultant fuzzy sets, that is also graphically. Now, here again another example. So, this is the fuzzy set A and its complement is basically complement will be this one is the complement. So, it is basically shown, it is there. So, graphical way of representing their operations is sometime more useful to understand. So, we have discussed it. Now, we will discuss about few examples, so that we can clear about our idea. Sometimes with a graphical representation we can express the operation, sometimes also mathematically we can express the operation. For example, say suppose A is a fuzzy set, whose membership function is defined by this expression. We can plot a graph, so graphical representation can be obtained accordingly. Similarly, another fuzzy set B, which is shown here. Now, if we want to know A complement, so A complement, this one, this is equals to 1 minus mu A x. So, this means is basically 1 by 1 plus x. So, this basically we can say this is mu A complement x, this is the membership function of the resultant fuzzy set. Now, likewise mu B x and its complement can be obtained, and graphically if we plot, then mu A x can be plotted like this. So, it is mu A x and mu B x, that can be obtained like this, the mu B x. Then the union of the two fuzzy sets A and B is basically, this is the union, and if the intersection, then intersection can be obtained by this one. So, graphically both can be obtained as well as mathematically it can be obtained. Now, the idea about these fuzzy operations is more meaningful. Now, we know every fuzzy set is basically expressed by certain meaning, this is called the linguistic hedge. Now, for example, say suppose A is a fuzzy set and B is another fuzzy set, A basically the cold climate and B is the hot climate representing with their membership function mu x and mu B x. So, the two fuzzy sets can be represented graphically using this shape, this is the A and this is the set B. Now, there are, so operation whenever we perform on A and B has the meaningful representation that can be obtained like this. Say if we know the fuzzy set cold climate or hot climate, then we can know the fuzzy sets not cold climate. It is basically complement of the cold climate, or not hot climate is basically complement operation of the hot climate. Extreme climate is basically is the operation of both, that means it is union, and pleasant climate is basically intersection. So, this is represented here by this. So, not cold climate is this one, not hot climate is a complement B, and extreme climate is union, and then pleasant climate is this one. Now, graphically the same thing can be shown also here. If so, these are the two fuzzy sets A B. The extreme climate that can be obtained by the plot, this is the resultant graph of the fuzzy set extreme climate, and this is the resultant fuzzy set of the pleasant climate. Now, this example basically shows you that how the different operations is meaningful in the context of fuzzy sets. Now, okay, let us stop it here. So, these are the different fuzzy set operation, and we will discuss the other things in the next lecture. Thank you.